Hello, I'm Edgar Kramer from Soundstage Australia. Today I'm joined by Dr. Matthew Webster from YG Acoustics. Good morning, Matthew.
Good evening from here. It's good to talk to you.
Good to talk to you. Um, um, Matthew, YG Acoustics is one of the few companies that builds its own drivers. Can you discuss the engineering, some of the key engineering aspects of the lattice tweeter and the Billet core mid-range driver used in the Carmel 3?
Of course. Um, I think the fact that we make our own drivers sort of reflects our approach to everything in manufacturing. I think it was only a handful of years ago that we stopped making our own screws. We very much believe that every part of the loudspeaker to get the performance that we want has to be driven by our design and our requirements and our material requirements. And we have an amazing machine shop in Denver. I think it's unrivaled in the audio industry. The CNC capabilities we have are ridiculous. If we look at each one of the drivers, probably the biggest innovation that we had with our reference 3 range was this lattice tweeter. There's so much science behind why different tweeters sound different, and it is generally true that fabric domes have smoother and more acoustically acceptable to human ears breakup characteristics as they head towards frequency extremes, but they tend to not have the extension. Their breakup modes tend to come lower in frequency because they're not as stiff as a material. There's, again, tons of science behind that and some really amazing things about why they do that, but let's just stick to the fact that they do. From our point of view, YG now, 7 or 8 years ago, came up with this billet dome tweeter, where there was an airframe that we machined out of aluminium, a very, very light frame that would go underneath the fabric dome and would support it through its first 2 breakup modes. So the little frame, it weighs just a few milligrams. It just sits under the fabric dome, and it attaches directly to the voice coil. So what this does is it retains a lot of the very harmonious breakup characteristics of the fabric dome, but it pushes the frequency response way, way higher. And it maintains a very good distortion characteristic as you start to approach that breakup. The first billet dome tweeter was already pretty revolutionary. We had the benefit when I started with YG in 2020, we were bringing a lot more computational and scientific firepower. And so we could look at this not only from an engineering perspective, but understanding much better now through our proprietary research, what human ears care about in that frequency range. We could design a new lattice airframe and pick a new material for it that would let it be a massive step ahead of our old billet dome tweeter. So we started off with quite a lot of scientific theory and some initial ideas which were based on the first breakup modes. We determined the breakup modes by simulation. We verified them using high-speed photography. It's amazing watching. You can get these incredibly high-speed video cameras now. You can actually watch how the dome is breaking up as it heads towards higher frequencies. And then we took those prototypes and we spent a fortune on cloud-based GPU simulation. We use Amazon's EC2 servers, and we can use this firepower. Each one of the servers that we can use 20 years ago to being the most powerful computer in the world, and you can take 6,000 of them within a few minutes. That's if you're lucky. Typically, we would take a few hundred. These just let us hit this with so much detailed simulation of exactly how it would behave. And not just, it's like everything in the design of our speakers. We don't design it using just sine waves at single frequencies. We look at how it behaves with very complex multi-frequency music. We play high-resolution music through it and see how it behaves. What were our aims? Our aims were to push the breakup modes even further up the frequency spectrum, so we have an extended frequency response. Very importantly, we wanted a very smooth phase response so that the phase characteristics against frequency continues to be very smooth and very predictable. Then we wanted to look at controlling the dispersion of the tweeter at very high frequencies. As frequencies go higher and higher, it's an inevitable consequence of physics that you end up beaming the frequency over a tighter and tighter range. We wanted, through the combination of this lattice airframe and the shape of the waveguide around the tweeter, to try and fight against the limitations of physics and see what we could do to keep the tweeter response even over a wider angular range. So you hear, I think for me, the dream loudspeaker, if you have a loudspeaker where your head has to be here and it's great, and you do that and it doesn't sound good, that's a terrible failure. It should be something that you can enjoy, your friend sitting next to you can enjoy, people walking through the door of the room can enjoy, and that wider angular response is a key part of that. So it does all of these things. It's a very special material, it's machined in-house, it still weighs a very, very tiny amount, and it's attached directly to the voice coil, and it sits behind the fabric dome. With the rest of our cone drivers, we want to, the best driver for any purpose inside a speaker is effectively a full range driver, because no matter what frequency range you pick, you want it to be distortion free way off towards the edges, because that means that the chunk that you're using is pretty well perfect.
Sure.
When we looked at the drivers that were available 15 years ago at YG, the only conclusion we could come to was that we needed to make the cones ourselves, because there's so many things you can do if you have sufficiently precise machining. If you look at our cones, some of our cones are lighter than paper cones, but they're so strong that you can actually stand on them. If you're careful not to have any shear, the strength in pure compression is unbelievable. The actual cone sides are down to 0.2 of a millimeter. They're incredibly thin, and yet the thing it acts like a piston over a huge frequency range. It's a perfect driver. And typically the first breakup mode is 3-4 octaves above the range where we use it. So you're not even starting to touch that. And so that's why we went down this path of milling our own drivers. Every iteration of these drivers has got better and better. And the drivers which are in the latest reference 3, and you find those same drivers in our peaks range, the shapes of the cones, and there's this incredibly delicate bracing structure that we machine into the back of them. The thing starts as a billet of aluminium, and then we mill the whole thing down till it weighs just grams and is the cone that you see there. We're working on some amazing technologies. I think hopefully in the next year or two we'll have even better methods of making cones stiffer, and still out of aluminium, but stiffer, and even pushing it further. But every single driver inside our speakers is an in-house machined aluminium cone, and each one of them has crazy behavior. Even our subwoofer, our big 32 centimeter subwoofer driver, it's if you defeat the low pass filter on the subwoofer, it's a perfectly credible full range driver. It's amazing what you can get out of these aluminium cones. They're so light and so stiff.
So with a full billet of aluminium, what is the waste recycled into?
Absolutely. Aluminium in that sense is an incredible material, because the recycling path for aluminium is relatively energy efficient and economically very good. What we do throughout our factory, every last shaving is collected and recycled. It makes good environmental sense, and it makes very good economic sense, because you get a very high fraction of the value back for recycled aluminium because the recycling path is so efficient. Sure. Now, Yes, we're always working to make that even less because it would be great not to have to recycle it. And
Sure.
we're a luxury product. Our energy footprint in making these speakers is too high, and anything that I can do to reduce that, I'm trying to do. That's, again, I talk about new technologies for drive units. In the past, we've been unable to achieve the performance that we have with machining these cones in any other way. And Lord knows we've tried. We've looked at every possible way we can do this. It's crazy to start off with this billet of very expensive aerospace aluminium and turn it into a few grams. It takes so much time. It takes so much ingenuity. I'd love not to do it. And we have some incredible new approaches that, with the benefit of the computational modeling that we have, we can hopefully avoid that in the coming years.
Sure. Okay. I wanted to touch on the crossover design because, in layman terms of my limited speaker design experience, assuming the Carmel 3's waveguide aligns the acoustic sensors of the tweeter and the mid-bass driver, plus the fact that it's such a tight phase alignment, 5 degrees. Is this a first order crossover design, or can you just elaborate on the ultra coherent crossover design in Carmel 3?
It's frustratingly difficult to explain because it's like nothing else. As it happens, okay, we look at our loudspeakers holistically. So we don't design the loudspeaker and then design the crossover. We start off with the cabinet and the drive units, and we build a model of finite element model of all of those, and then we model the crossover down to a physics level. So we don't model it as electrical components. It's not modeled as a capacitor or an inductor. The inductor is a loop of wire with a dielectric. We model the circuit board. We model every track on the circuit board. The capacitor is a Swiss roll of a dielectric with either foil or a sprayed coating with end caps of a particular geometry, blah, blah, blah. We then run a physics model with a very, very fine time slice to model how transients and electrical signals propagate through this. The hysteresis loss, how the magnetic fields, the magnetic fields from each component interact with every other component. It's not just the inductors interacting with each other. Anyway, why am I saying all of this? Because, as it happens, the positioning of the tweeter and the acoustic center of the mid-range driver in the Carmel are aligned. They're aligned to within a very fine tolerance. They don't need to be. We could actually move the tweeter 2 inches forward and pretty much keep the same performance level, because we could then design a delay into the crossover with almost no acoustic impact that would realign them from a signal perspective. The crossover topologies are nothing like any other crossover topology I've seen in loudspeaker design. They are very carefully designed so that we have a very high order roll-off. So the effective roll-off that we achieve is 3rd order or higher, and typically 4th order between the drive units. But that's a combination of physical design and electrical design. We'll use the cabinet, the natural cabinet resonances. We'll use the characteristics of the drive units to achieve a much higher roll-off with a very benign phase behavior. So if you were to look at the topologies, they don't look anything like a conventional crossover. So it's a difficult, I'm not trying to avoid answering the question.
Sure.
It's just a very strange design, and it makes no sense unless you control the drive units and the cabinet and even the wire that runs between them. Everything plays a role. I don't think there's a single part in those speakers that doesn't do exactly what it needs to make the speaker behave at the level that it does.
Sure. So you mentioned the fact that you machine the cabinets in-house. Is that the same case for the entire reference series? And
yes.
Yeah, okay. So you obviously CSC machine.
Yes.
With various degrees of machining.
Every single part in our reference speakers, every aluminium part that you find in any YG speaker is machined in-house. In the Peaks range, which is our entry range, the cabinets are made out of a dense resin fiber that is made by specialist European manufacturers, but every aluminium part for Peaks and every part of reference is machined in-house. We've invested a huge amount in YG over the last 4 years. It's just over 8 million by this point. We have, to my knowledge, by far and away the most advanced machining capabilities in the audio industry that I've seen. The workflow that we have is all of our material comes in as very high grade. We only use aerospace grades of aluminium and very selective ones. For us, it's important that the crystal structure is something that we can rely on as well. So there's specifically heat-treated grades. We have this amazing machine. We have a water jet that cuts the aluminium.
Right.
This thing, if you haven't experienced a water jet, it's something that's worth visiting to see. It can take 10 centimeter thick aluminium and cut it like it's butter. It's just a very, very high pressure jet of water which has an abradant in it. We use a garnet abradant, and it will, to an incredible precision, cut this into pieces. We then have a range of CNC machines. We use the latest generation of DMG Mori CNC machines with very large working volumes. And we've selected them because all of their scales are temperature corrected, so they're accurate to within 1,000th of a millimeter, absolutely reliably. Why is that important? Well, because to do what we want to do, the tweeter waveguide is a perfect example. It actually has to be that precise to do what it wants. The placement of the tweeter, the actual tweeter face in the middle, has to be that precise. And it gives us the variety of materials we can machine and the quality to which we can machine them, and the quality control we can have is unrivaled. And it gives me these capabilities in design that would otherwise be impossible.
Sure. Okay, so I wanted to ask about the Carmel 3 cabinet. Is the aluminium, the panels, are they damped or for resonance in any way, or do you even consider that a necessity? What are your views on that cabinet design?
To make sure that the cabinet doesn't resonate is a very important part of speaker design. Sorry, I feel like I'm patronizing with an answer like that, but no, it's a critical aspect. We design every panel. You'll notice in the Carmel, every panel has a gentle curve to it. The design is already optimized to minimize the resonances. So what we do is we make sure there are no high Q resonances, no sharp resonances anywhere in the cabinet structure. We then have a very clever variety of braces and connectors that hold all the pieces together, which further damp the cabinet. We try very hard to minimize needing to stick damping material inside our speakers, because in general that shows a design flaw that you could have dealt with beforehand. So that's not generally the approach that we take. When you head to the higher end reference models, we use constrained layer damping with either 2 or 3 layers of aluminium with this incredibly clever polymer that we've got between them, which is across a huge frequency range, incredibly energy damping. But in the case of the Carmel, it's just a single skin, and it's the design which eliminates those resonances.
Right, okay. I'm interested in how you balance objective things like acoustic engineering and simulations and measurements with subjective listening. How do you go about that?
Well, there's no point in the first two without the last one. So what we're not simulating to make laboratory instruments. Whenever in audio I've found people who concentrate on traditional laboratory metrics, it's very easy to lead yourself astray. You can come up with a perfect DAC or a perfect loudspeaker, if you look at sort of frequency response or something else, and the sacrifices that you make to get that are very audible sacrifices, because your ear doesn't care about the same things as the laboratory instrument. When I started working at YG, the first 6 months was just spent listening and measuring at the same time, but understanding what it is that makes loudspeakers and audio systems make magic. Is it make magic? If you get the setup right, the right speakers, the right amplifier, the right recording, everything in the right room, everything disappears. And it's this amazing, so it's a phase transformation. It goes from being okay to being ridiculous. You're there, and it's so easy. Even talking about it, I can feel the goosebumps. The fun thing was working out that this is the same for everyone. When a system makes goosebumps, it makes goosebumps for everyone. And the first 6 months was working out what makes goosebumps. And it's certainly not a dead flat frequency response. That's a nice thing to have. I'm not saying don't have it, but as it happens, it's way down the league table of what's important. So what we're trying to do is understand how humans and how we, because in the end, the fun thing about an audio company is you're a consumer as well. I love making this stuff because I get to listen to it. Sure. You understand from a scientific and engineering perspective what you have to do to make the goosebumps, and then you build your simulation and your theory and the way you guide your engineering to answer that question. It's got so much better because from the very first speaker I was designing this way, we would build one physical prototype, measure the life out of it, listen to it, and then build maybe 10 or 20 virtual prototypes that would be better and better and better, build another physical one. And each time we would learn new acoustic, new human things about what makes it even better. These days, that loop is tighter and tighter. With the XX, which is our latest model, the first prototype is the production version. We built the prototype, it met all of our modeling requirements. We listened to it, we couldn't stop listening to it. We were perfectly happy, we made it a production model. So it's a very long answer. It's always, the only point of this is the subjective experience. And you use all the science to do your best to deliver that subjective experience.
Sure. So the XX being the new speaker, will there be trickle down with the lessons that you learned in the design of the XX that will trickle down to the rest of the speaker range, or is that something that is going to be purely a technology-based thing that has to be within the context of XX? No. We are. I think trickle down is the wrong verb. It's like gush down in terms of how we move our technologies. Interestingly, the transition to reference 3 was a case of trickle up. We learned so much designing the Peak series, which was our entry range, that's why, from a commercial point of view, my love for how this stuff sounds makes me keep on making stupid commercial decisions. Rather than, the best thing to have done would have been to trickle out upgrades for reference 3, upgrade 2 models, then upgrade another 2 models the next year, etc. What we discovered making Peaks, I just couldn't hold it back. I'm just like, there are massive improvements that we can make to reference given what we've learned here. And that's why last year we introduced the whole set of reference 3. Every single model was updated. That was, for everyone in YG, one of the hardest years we've ever worked to update every single speaker. Hardly a part wasn't changed. It was an end-to-end redesign completely. And the only thing that we kept roughly the same is the exterior look, because YG has a very long commitment to letting customers upgrade. So with a couple of exceptions, almost any YG speaker can be upgraded all the way through to the current version. And it's something that we believe in. And that guided the physical design. Okay. Would you say YG Acoustics has a signature house sound that carries across from the lower to the upper tier models? And if so, how would you categorize that sound?
Yes, I think there is. I think there is because my ears feel it, and a lot of our customers and a lot of our dealers and distributors were very pleased that peaks and reference as a whole end-to-end set all sound very much like they come from the same approach. I had the pleasure about a year ago of sitting for the first time and listening to every single one of our models in a row in the same room with the same amplification. And you could hear the differences and the progression through the chain, but the house sound was definitely there. Now, how would I characterize it? A lot of it, for better or worse, is what I like in sound. This sense of accuracy and detail, this sense of liveness. For me, there's a sense of pace when something is good, especially with live recordings, really good recordings. When you have that pace, and there's so much science behind what makes that pace.
Sure.
That is the electrifying thing for me, and that tends to lead to a very realistic mid-range, a very fast sound. So that's a key. For me, I'm not a believer in absolute accuracy to a point that it will hurt. I think the best loudspeakers should make the best recordings sound incredible, but if they can at the same time make bad recordings sound okay, then that's good as well. We're not building monitors for recording. They're not meant to lay bare every deficiency in what you're doing. They're instruments of joy. And so for me, I think I like all the detail to be there. The placement of the soundstage is incredibly important in this suspension of disbelief and this magic. But a good system you can listen to for 8, 12 hours and carry on loving it. You shouldn't listen for half an hour and then start to have a headache. So yeah. That's key. And there's a final thing, which is, sorry, this is going to sound like it's all good, but I listen to an awful lot of electronic music. I listen to everything, but electronic music, especially when I'm working, is something that I like. And that bass quality, that phase coherence from bass to mid-range, the ability to produce this physical slam that you feel in your chest, whether it's electronic music or timpani, what that is telling you, if you actually feel the slam, you can almost feel your hairs moving as the pressure wave goes over you. That's showing that you have timing and phase coherence all the way up from 20 hertz to a few kilohertz. And when you achieve that, it's such a beautiful thing. It makes the bass just come alive. And that drives things. So all of these are things that, from our point of view, drive the speaker design. But I don't know whether that's something that you can really describe as a house sound.
I think you've done that very well. Thank you. And on that note, I'd like to thank you for joining me, Matthew Webster from YG Acoustics.
Thank you very much for having me. It's a pleasure.